Hey guys, welcome back. I have a drawer of electric motors that I use on various projects. But this time, instead of just using an old one, I wanted to see if I could build one from scratch. I don't have a CNC machine, but I do have a 3D printer. So I wanted to know, is it possible to 3D print an electric motor? The materials we'll need are the copper wire, filament, an ESC and some tools, and the magnets. Now let's go to Fusion 360 and start designing. And here is the model we ended up with. I went for a radial flux design for the motor. Our stator has 6 slots. And our rotor will have 8 20mm neodymium magnets. Export the completed STL files from Fusion and import them into Bamboo Studio. Use the default settings and send them to the printer. Okay, so here is the printed rotor, it's the 20mm neodymium magnets. We're going to slot the magnets into the rotor like that. And here is all of the magnets in the slot. I marked north-south, north-south for opposing poles. Onto the stator now. We're going to do 50 turns per stator. The wire over to the opposite coil and wrap it anti-clockwise. Okay, now that we have our stator fully wound and we have the endings sandpapered off, we are going to essentially join A2, B2 and C2 in a Y configuration. Then we have 3 phase outputs, A1, B1 and C1. So I attach the positive to phase A and the ground to phase B. And what we should see is it's snapped to a certain position. So I've it at 5 volts and 1 amp. So you can see we got the smallest possible amount of movement. So our number of windings, our thickness of our wire, the amount of magnets we picked, they're all possible issues. Check the resistance, all similar resistance, maybe one slightly more. The most likely issue is that the plastic PLA core is not ferromagnetic enough, so it's not creating a strong enough magnetic field. So is there anything we can do to make this electric motor work or improve it somehow? So probably what the easiest one to do is to insert a iron screw into the core of each stator. We can have stator cores that are slightly easier to work with, easier to wind, and then we can insert an iron screw into the core. The idea for this new stator design came from this great video from Levi Janssen. Check it out, I left a link in the description. 50 turns and I will sand off the endings. Okay, yeah. We could redesign our current radial flux motor and replace these sort of a new design that has a screw insert, possibly, around the edges like this. Or we can use it as an excuse to try a different design. Let's go back into Fusion and redesign our stator and our rotor. And here is the new stator design. Instead of a flat base, I've decided to go for this flower structure. With the stator core as we showed earlier, they can easily be screwed into the 6 slots. And I used a similar design for the rotor. This time it will use 8 18mm disc magnets. add a base, some magnet stoppers, and our design is finished. Export and print. So the rotor has 8 slots for disc magnets. They have a small lip at the bottom so the magnet doesn't fall through. Just caught at the end there. So here's all 8. They are alternating north-south, north-south, and I just put a screw in the center. This is our new stator, this new flower-looking shape, our 3D printed stator coils. They will all just fit in the slots, fit perfectly into the hole. We can use the screws to lock the stator coils into the stator. Hopefully we'll improve the magnetic field and make it stronger. We are going to wind all 6 of these stator cores, and we'll also use a 28 gauge 3mm. We should be able to get far more turns from this copper wire on each stator coil. Let's start winding our coils. We will wrap the first one in a clockwise direction. I don't know the exact number of turns, it'll be however many turns fill up the stator. So a lot more turns. We can sand off the endings. We repeat the process for the other 6. This is our completed stator. Each one is wound clockwise, anti-clockwise, clockwise, anti-clockwise. We join the bottom wire of the A1 and A2, so the opposites, and we connect them in series. Just wound them here without soldering, just to test the endings. So our phase endings this time, A1, C1 and B2. That triangle spread out. Our Y neutral point is going to be B1, A2 and C2. Those 3 are joined together. It can stay messy for now and we can tidy it up after. We'll do the same test as we did for the previous radial flux motor. So our base, our stator, our rotor, little caps to stop the magnets. Just put these 3 together. I can spin freely. The first test, just like the last time, put on the power. We should hopefully see some movement on the rotor. Oh. That's what it should look like. Yeah. So this is phase A and phase B, and let's just quickly test phase A and phase C together. Again, you see that snap to the next position, B and C together. The next one. So we have our motor, we have our phase endings connected to the SE connected to our variable power supply, and we have the Arduino giving it the PWM signal. That's good. You can hear it, it's trying to spin, but it's not starting properly. Only when I give it a push does it go. There. I'll try to increase the speed. 300. 400. Wow. I wonder if we can build our own ESC and see if we can smoothly start it up that way.
A few moments later.
Here is our custom ESC. P-type MOSFETs for high-side switching and the N-type MOSFETs for low-side switching. Green phase A, white phase B, yellow phase C. I 3D printed some more of these magnet caps. We have 9 volts, 2 amps, we have our custom ESC, we have our Arduino, we have our motor hooked up to the phases. So the first test is going to be phase positions. We have our different phases A, B and C. And the main loop is essentially wait for a certain delay and then activate a phase. So you can see the different phases here. If we type in any number between 1 and 6, we can test that individual phase. If I type in 1, we will activate this phase 1, which is A high, B low, and it should snap to that position. Then when we type in 2, it should snap to the next phase, which is C high, B low. So one cycle, phase 1, 2, 3, 4, 5, 6, we should end up somewhere like here. So let's test it. So in the code, if we open up our serial monitor and we connect our power supply, if we type in 1 and enter, we should see the motor snap to that position. And 2, and 3 to phase 3, phase 4, phase 5, and phase 6. Each phase is working exactly as we wanted. So now if we keep going with that, phase 1, 2, 4, 5, 6, that's 2 loops of 2 electrical cycles. And if we just complete the loop, we're back to the start again. So full rotation. So our custom ESC is working. We are going to take this code, activate the phase, wait a certain delay time, and then activate the next phase. If we do S, you can see it start to spin up there. But now we can increase the speed each time by typing in M, and that's going to reduce the delay even more. We started at 60, we accelerated up till 10 millisecond delay, and now we're reducing by 2 milliseconds each time. Now we're on 8, and let's increase it to 6 milliseconds. And now let's increase it to 4. Hit the limit of our current open loop code. It doesn't actually know where the motor is, it's just running the loop round and round. So once it gets out of sync, it can't recover. Reduce the speed back to 6. It took some time, but we managed to get our 3D printed electric motor to work. If you have any idea why the first radial flux design wasn't working, or suggestions for this new design, please let me know in the comments and I can make a follow-up video. See you in the next one.